Alright guys, in this video I'm going to show you how to complete the 2D projectile vector practice. So let's read the directions. First we're going to solve for the magnitude of the resultant initial velocities. Then using at least 3 different colors and the head to tail method, we're going to draw the vectors. We're going to use a protractor to measure the angle between the hypotenuse and the horizontal vector. Then we'll show that sine, cosine, and tangent of the angles equal the ratio of the corresponding side lengths. Show all work and include units. So for this, to get started, you need the handout. You need a protractor with a ruler side, a pencil. I want you to do everything in pencil. 3 different colors. We'll use the colors at the end. In this case, I have red, purple, and blue. And then we need our trig functions. So if we don't remember, sine of the angle is equal to the opposite side over the hypotenuse. Cosine of the angle is equal to the adjacent side over hypotenuse. And then tangent of the angle, where the angle is theta, is equal to the opposite side over the adjacent. So we're going to show using measurements that these relationships are true. I'll do number 1 with you. Using in here. Number 1. In number 1, Jordan kicks a ball into the air. The ball has a horizontal velocity of 7 meters per second and an initial vertical velocity of 3 meters per second. Every 1 meter per second is going to be 1 centimeter. So I will start by drawing the horizontal velocity. It's 7 meters per second, so it needs to be 7 centimeters long. So making sure my protractor is level, I'm going up to 7 centimeters, which is right here, along the number 7 line. Have my arrow drawn, and this reads, I'm going to label this 7.0 meters per second. I'm going to put the head of this vector to the tail of my second vector. My second vector is a vertical vector, 3.5 meters per second. That's going to be totally vertical, so I will line up my protractor here. And making sure I'm totally vertical, draw a line that's 3.5 centimeters long, put the arrow here, 3.5 meters per second. And then using this side of the protractor, I'm going to draw the remaining side, which will be the hypotenuse. And I have my arrows here. We can get this remaining side. I can choose to measure it, or I can calculate it. In this case, I'm going to calculate it. A squared plus B squared equals C squared. A and B are the shorter sides of the triangle. C is the length of the hypotenuse. So if I'm looking not for C squared, but for C, I can take A squared plus B squared, take the square root. That'll give me C. In this case, I will have 7 squared plus 3.5 squared. I will take the square root, grabbing my calculator, second x squared for the square root, that's 7 squared plus 3.5 squared. That gives me a side length of around 7.8 meters per second. Now I've rounded, so this is not going to be, the answer that I have is not perfect, but that's okay, we can still measure the angle. To measure the angle, you'll see the protractor has a hole right here. You're going to line up the hole with the position where the hypotenuse and the horizontal vectors, they meet down here. And I make sure to have this line that goes through the hole, this is going to be flat against the horizontal vector. Now what you should notice is my hypotenuse now points along an angle. The angles are along this side of the protractor. Yes, it says 170, but notice it also says 10. It goes in 2 different values. So this would be 10 degrees, 20 degrees. This long line is 25, 26, This is all around 27 degrees. I'm going to zoom in here more so you can see. See where my hypotenuse is pointing to that vector. So again, with this center line level to the horizontal vector, I'm going from 20 to 30. That's the angle is in between 20 and 30. I see it's 25, 26. It's about 27 degrees, this line. So I'm going to write, I'm going to label this angle like this. This angle we're going to call theta. That's the Greek letter. It's a circle with a horizontal line through the middle. And that's around 27 degrees. Now what we're going to do is show that sine of 27 degrees is approximately equal to the side that's opposite to the angle. This is 3.5 divided by the hypotenuse, which is 7.8. The sine is opposite over hypotenuse. I need my calculator, and I need to check that my calculator is in degree mode, so I'll go to mode. Right now it's in radian, so I scroll down, I highlight degree, I hit enter, second quit, and I'm going to get the sine button. Sine of 27 equals 0.454. So I'll write that just below here at 0.454, and that should approximately equal 3.5 divided by 7.8. So I will calculate now. 3.5 divided by 7.8. Sorry about the glare. And I get 0.449. So that is approximately equal to 0.449. I'm going to box that in so it's easy for me to see later. The reason there's a slight discrepancy is because our measurements are not perfect. There is some error in how I'm measuring the angle. I can't do everything perfectly, but I can show that they are approximately equal. We'll do cosine next. Cosine of 27 degrees should approximately equal my adjacent side. This is the side that helps form the angle. In this case, that's 7.0 over my hypotenuse, 7.8. Because again, cosine of the angle is adjacent over hypotenuse. Coming back, I'm going to get cosine of 27 degrees. My calculator is still in degree mode. I'm going to type cosine. Cosine button is here. Cosine of 27 degrees. Close my parentheses, hit enter, and I get 0.891. So on the paper I show 0.891, and that should approximately equal 7 divided by 7.8. And it does. I get 0.897. That's pretty close. So I'll box this in, show my values. Last one, we do tangent. Tangent of 27 degrees should approximately equal my opposite side, opposite to the angle, that's 3.5, over my adjacent side, 7.0. This should equal 3.5 over 7.0, because again, tangent theta is opposite over adjacent. So I'll plug into the calculator. Calculator still in degree mode. Tan, the tan button is next to the cosine button. Tan 27 equals, get the value, 0.5095. I'll round it to 0.51. 0.51 is approximately equal to 3.5 over 7.0, and that's 0.5. So those are approximately equal. If I could measure perfectly with my angles, they would definitely equal each other. Now for the last part, we are going to highlight these vectors using our 3 colors. So just using the flat edge of the protractor, I will highlight this vector. This is my 7.0 meter per second vector. I will highlight my vertical vector, the 3.5 meter per second vector. And then finally, third color for the hypotenuse. This just helps us cement our head-to-tail method for vector combinations or for vector addition, 2D vector addition, 7.8 meters per second. Thank you for watching this video. I hope you found it helpful and study well.